Okay, hello. So this video will look at finding unit vectors in a couple different dimensional spaces. Okay, so remember first that that we have the dot product is given as a sum of products, and the dot product of a vector with itself is therefore a sum of squares. So it's positive, unless we're in space-time and the last sum becomes a minus sign, and then we can have light-like photons. But then the length of a vector is then the square root of that positive number, the sum of squares. Okay, and so a unit vector is just a vector whose length is 1. And so you can just take any vector, let's say that vector has length, maybe its length is 3.2, and just shrink it down until it has length 1. And the way you shrink it down is you just take the vector, let's say this is w, and then the unit vector in the same direction, usually called w hat, is formed by just taking w and dividing every component, dividing every coordinate of w by the length of w. So that just shrinks it down to 1. And this actually works in both this. So if you had a really tiny vector w, and actually to get a unit vector you need to scale it up. Well, still, the unit vector w hat is just the original vector w divided by its length. Now you're dividing by a very small number, which actually makes each component bigger, exactly to make it a length 1 vector. Okay, so the unit vectors are the vectors on the unit circle. All these vectors are unit vectors. And so you can think about it as like any vector, just shrink it down to be on the unit circle. Any vector over here, just shrink it down until it's on the unit circle. Any vector over here, just shrink it to the unit circle. And that actually works in 3-dimensional space too. I'm going to try to make this 3-dimensional space. I don't know, that was pretty bad, but any vector, just shrink it down until it touches the unit sphere. And that's a unit vector. Okay, so well, here's this vector. I mean, usually if something's in R1, we don't even write these parentheses, but I wrote them just to be similar to the others. You can, of course, write any symbol you want, as long as you communicate it well with other people. If it's just for yourself, then I guess you can write whatever you want and you don't need to communicate it well, as long as you're remembering what it is later. Okay, now the length of this vector is the square root of the sum of squares, well, of the one component, which is just 3. And you can see that this is the absolute value of the number minus 3. And so this symbol for length, just as the absolute value symbol of a real number, ends up being the same thing. Right? Now if we have 2 components and we're in R2, now it's not just the absolute value anymore, it's the square root of the sum of squares, and we get square root 13. And right now all I'm doing is just calculating this denominator that I'll need later. And so here the square root of the sum of squares of 3 numbers, 9, 4, 49, give me square root of 62, 9, 4, 49 plus 1 gives me the square root of 63. And so then what I do is just take each of these vectors, divide it by its length, and that gets a unit vector, usually called with a hat, usually. Okay, so you could just write it like this, or you can actually put the denominator inside, or you can even just write it as like a fraction outside. This is like we'd call this a scalar. It's scaling the original vector. And so, this thing here, this expression, is a unit vector because, it's a non-unit vector scaled by the right amount so that the overall thing has length 1. And of course, let's check. We can take the sum of squares of these. So what's the first one squared? Well, it's 9 over 62. What's the second one squared? Well, it's 4 over 62. What's the third one squared? Where it's 49 over 62. 9 and 4 is 13. 10 plus 49 is 59, and 3 plus 59 is 62, and of course we get 1 equals 1. This is a 1. A terrible 1. I'm never sure how to write 1s. There's many options. Yeah, anyway. Okay. Is that basically it? Yeah, that's it. Okay, that's all on unit vectors.